The ketogenic diet, once a fringe therapeutic tool for epilepsy, has surged into broader medical relevance due to its profound effects on brain metabolism. Characterized by high fat, moderate protein, and very low carbohydrate intake, this diet fundamentally shifts the body's energy landscape. Instead of relying on glucose, cells, especially neurons, begin to use ketone bodies as their primary fuel source. This metabolic adaptation not only alters systemic energy balance, but also profoundly impacts glycogen dynamics within the brain. Recent research has started to explore how this shift might help reduce abnormal glycogen accumulation and possibly slow neurodegeneration, suggesting a novel protective mechanism in conditions where energy metabolism goes awry. In the brain, glycogen is not as abundant as in muscle or liver, but it plays a crucial role in buffering energy demand, especially during periods of stress or glucose scarcity. Most of this glycogen is stored in astrocytes, the brain's support cells, which can break it down into lactate or glucose intermediates and shuttle them to neurons as needed. Under normal conditions, this system is tightly regulated. But in several neurodegenerative diseases like Alzheimer's, Huntington's, and Lafora disease, disordered glycogen metabolism has been observed. In some cases, there is an abnormal buildup of glycogen or malformed glycogen-like structures, sometimes referred to as polyglucosan bodies, which can interfere with cellular function and contribute to oxidative stress and inflammation. This is where the ketogenic diet presents an intriguing opportunity. By severely restricting carbohydrate intake, glucose levels in the blood and brain drop, forcing cells to adapt to alternative fuels, primarily ketone bodies such as beta-hydroxybutyrate and acetoacetate. These molecules are not just passive energy sources. They also exhibit signaling properties that influence gene expression, mitochondrial function, and inflammation. Importantly, in the absence of high glucose, the demand for glycogen synthesis drops, potentially preventing the abnormal accumulation of glycogen and its harmful byproducts. In this metabolic state, astrocytes may shift away from active glycogen storage and focus on supporting neurons through ketone metabolism and lactate shuttling. Neurons, in turn, become more efficient at using ketones, which produce more ADP per unit of oxygen than glucose does and generate fewer reactive oxygen species. This cleaner energy supply could help stabilize mitochondrial function, reduce oxidative stress, and protect against excitotoxicity, all critical features in slowing the progression of neurodegenerative disease. Moreover, ketone bodies themselves have been shown to inhibit histone deacetylases (DACs), leading to beneficial changes in gene expression that upregulate antioxidant defenses and neuroprotective pathways. These epigenetic changes further support cellular health in a low-glucose environment. Studies in animal models of Alzheimer's and Parkinson's disease suggest that ketogenic diets can reduce amyloid burden, improve motor function, and enhance cognitive performance. Part of this benefit may be due to the reduction of abnormal glycogen stores and the metabolic rebalancing that follows. But there are cautionary notes to consider. The long-term impact of chronically low glucose levels on brain function is not fully understood, especially in developing or aging brains. While ketogenic diets may reduce toxic glycogen buildup, they may also reduce the availability of glucose for certain brain regions that still rely on it. Not all neurons adapt equally well to ketones, and excessive dietary restriction can potentially impair mood, cognition, or hormonal balance in susceptible individuals. Furthermore, strict adherence to ketogenic regimens is difficult for many people, and improper implementation can lead to nutrient deficiencies or elevated lipid levels. Still, the therapeutic potential of ketogenic diets in modulating glycogen metabolism in the brain remains compelling. By reducing glucose availability, this dietary approach may offer a way to bypass defective glucose pathways, limit glycogen-related neurotoxicity, and offer neurons a more stable, protective fuel source. As we deepen our understanding of how glycogen dynamics influence brain health, the ketogenic diet stands out not merely as a weight loss trend or seizure therapy, but as a metabolically precise intervention that may help address the root energetic imbalances seen in many neurodegenerative conditions. In a world where sugar overload and metabolic dysfunction are increasingly common, adopting strategies that improve brain energy efficiency may be key to preserving cognitive longevity. Whether through full ketogenic diets, cyclical approaches, or targeted use of ketone supplements, the ability to control glycogen accumulation and support alternative energy pathways may one day become a mainstream therapeutic option for maintaining and protecting the brain across the lifespan.